Hello everyone, my name is Antonio Silveti-Falls, and today I'm going to talk to you about non-smooth implicit differentiation for machine learning, a joint work completed with Jérôme Bolte, Tam Le, and Edouard Pauwels. Consider some smooth function f and an equation, f equals 0. In this case, our function f defines the circle in the plane. Implicit function theorems seek to address two questions. The first, can we find an implicit function g which solves our equation, at least locally? The second, can we compute the gradient of the implicit function g? The smooth or classical implicit function theorem due to Dini and Cauchy answers both questions positively. It says that so long as we avoid bad points, shown here in red, for which the gradient of f with respect to y is 0 or non-invertible, then there is a neighborhood u on which there exists a smooth implicit function g, shown here in turquoise. This answers the question of existence. The classical implicit function theorem goes on to state how we can compute the gradient of the implicit function g in terms of the gradient of f, shown now in orange. This provides us with a calculus for the gradient of the implicit function g. The motivation for our current work is to examine what happens in the non-smooth setting. The question of existence is addressed positively by Clark and others for locally Lipschitz functions. On the other hand, the question of how to compute the corresponding gradient-like objects in this setting is not addressed by past theorems, although it is now possible with conservative Jacobians and so-called path differentiable functions, which I will touch on later. Why do we care so much about a calculus for non-smooth implicit functions? In optimization, one hopes for an algorithm of the following form, where dx is some descent direction or surrogate gradient. For non-smooth implicit problems, our work provides exactly such an object and how to compute it. Now let's review what the Clark subdifferential actually is. The formal definition is shown at the bottom of the screen, although I think it's easier to visualize what's happening with a picture. Imagine you have some locally Lipschitz function here denoted by f. There are 2 points where this function is non-smooth, denoted x1 and x2. If we compute the gradient as we approach these points from the positive direction, shown in blue, and the negative direction, shown in red, then the Clark subdifferential is simply the convex hull of these gradients, shown now in purple. Notice that this is a set-valued object as we are in the non-smooth setting. We can now state the non-smooth implicit function theorem for locally Lipschitz functions. Given some locally Lipschitz function f and a solution x hat, y hat, for which every element of the subdifferential with respect to the second argument is invertible, that is to say, we can avoid the bad points shown in red, just as in the classical implicit function theorem, then there exists a neighborhood u and a locally Lipschitz implicit function g which solves our equation. We can do this for any point x hat, y hat, for which every element of the subdifferential with respect to the second argument is invertible. Since Clark's theorem effectively addresses the existence part of an implicit function theorem, let's turn to the calculus part. Consider some locally Lipschitz function f and x hat, y hat for which Clark's implicit function theorem holds with implicit function g. Recall from the smooth implicit function theorem that we have a calculus which tells us how to compute the Jacobian of the function g in terms of the Jacobian of f. It's natural to ask the question, can we have an analogous calculus of the form shown here now for the Clark Jacobian in the locally Lipschitz setting? Unfortunately, the answer is no. We need a gradient-like object that extends beyond the Clark Jacobian. Indeed, we show that there exists a piecewise linear function f, in particular, f is locally Lipschitz, for which Clark's inverse mapping theorem fails, and by extension, the proposed calculus for Clark Jacobians must fail as well. Let's quickly turn to defining conservative fields, the generalization of Clark's subdifferential that we will use for our non-smooth implicit function theorem. A conservative field is a set-valued mapping df which generalizes the Clark Jacobian to have a chain rule. Given a locally Lipschitz function f, a conservative field for f must satisfy three properties. The first is that it should always be non-empty, and ideally convex, although this is not a big deal since the pointwise convex hull of a conservative field is again a conservative field. The second is that the conservative field should have a closed graph and be locally bounded. The third and final property is that the conservative field should satisfy a chain rule along absolutely continuous curves. This final property is the most important because it allows us to rigorously model backpropagation and also allows us to use differential inclusion arguments to show convergence in a multitude of settings. We call functions like f, which admit conservative fields, path differentiable. This is a lot to take in, so I will summarize the take-home message in the following way. Conservative fields are gradient-like objects that faithfully model what is computed by backpropagation in practice, even with non-smooth activations like the ReLU function. With all these pieces in place, we can now state our non-smooth implicit function theorem. The first half of our theorem is exactly the same as the theorem of Clark, only now with locally Lipschitz replaced by path differentiable, and Clark Jacobians replaced by conservative Jacobians, shown here in the olive color. Indeed, the previous non-smooth implicit function theorem effectively addresses the existence part of our question. Our contribution is primarily the second half of this theorem, shown in orange, which describes a calculus telling us how we can compute a conservative Jacobian for our path differentiable implicit function g. The formula given is exactly the analog of the formula that one has in the smooth setting. Most importantly, because we use the framework of conservative fields, this calculus is compatible with backpropagation and algorithmic differentiation as they are implemented in practice. Shifting gears now to applications, let's discuss deep learning with implicit layers. An implicit layer is defined not by how it acts on the input to the layer, this would be an explicit layer, but rather an implicit layer is defined by which properties we want the output of the layer to satisfy. We can see the fixed point layers, as described in several papers shown here, as the infinite depth analog of conventional explicit layers. In particular, the theory of conservative Jacobians, along with our path differentiable implicit function theorem, allow us provable convergence guarantees in the form of Clark stationarity. This is to say that 0 is in the Clark subdifferential of the limit point of SGD with a vanishing step size almost surely. We provide a detailed argument of this flavor for monotone deep equilibrium networks in our paper. Another application of our work is to bilevel optimization. An important question in this field is how to differentiate the solution, here denoted as x, of a non-smooth optimization problem. Our theorem provides a possible solution. If we can find a path differentiable optimality condition, that is to say, some fixed point equation or solution mapping, then we can apply our implicit function theorem and calculus to the corresponding conservative Jacobian. This allows for rigorous convergence guarantees for several important settings, notably for neural networks with layers defined as convex optimization problems, but also for more classical problems like hyperparameter tuning of the lasso. For conic optimization problems, we can use the path differentiable normalized solution mapping, while for the lasso, we can exploit the fact that the solution must be a fixed point of the forward-backward operator and then examine when this is path differentiable and when the invertibility condition will hold. Finally, I want to talk to you about what happens if you ignore the invertibility condition of the implicit function theorem. You might be tempted to use the theorem if the element of the conservative field you compute with backpropagation is invertible without checking that every element is invertible as required by the theorem. As the following examples will show, this can lead to very undesirable behavior. Consider an optimization problem with a piecewise quadratic objective function, written in a way that we can apply the implicit function theorem. When we apply gradient descent to this problem, we get a pathological behavior in the form of a cycle for our gradient flow trajectory, due to the lack of invertibility. Although backpropagation is computing an invertible element at each iteration, the mere existence of non-invertible elements in the conservative field here results in a cyclic trajectory. We show the initialization in black and the gradient flow trajectory in red. You might wonder if this behavior can be avoided by taking a different initialization. However, this is shown to be false, as the plots on the right-hand side demonstrate. Our last pathological example involves optimizing a quadratic function in two ways. On the left, you see the explicit formulation of maximizing a quadratic form over R3. On the right, we have the same problem, but reposed as an implicit formulation that we can apply our theorem to. Unfortunately, the fourth power in the lower level problem will result in the invertibility condition being violated, although the two formulations are completely mathematically equivalent. On the left, we see the trajectory of the iterates given by vanilla gradient ascent applied to the explicit formulation of the problem. Meanwhile, on the right, we see a completely chaotic trajectory for implicit gradient ascent. It even looks like the Lorentz attractor. This behavior is a result of the lack of invertibility in the implicit formulation, despite the two formulations being equivalent. Thanks for listening to my talk.